Hello, my name is Taryn Edwards. I will be representing Group 2 along with Becca Travis, James Kratzberg, and Nick Rokos, and today we'll be talking about IC engines. This presentation will cover the experimental engine setup and the background, the work energy model used to analyze the system, the methods behind the two configurations of the system, an overall uncertainty analysis, and the next steps for configuration 3, the last configuration. In the experimental setup shown here, the 4-stroke internal combustion engine was instrumented with an encoder to detect engine and motor shaft position and a force transducer to detect engine and motor torque. The motor has basic RPM controls and external flywheels that can be removed, and the full system was controlled with a LabVIEW VI. The goal of this experiment is to determine system parameters and controls for a 4-stroke IC engine using the work energy model as a basis to characterize the properties and controls necessary for optimal power generation. This was achieved by performing experiments with 3 different motor configurations, as each configuration led to a new set of assumptions. During all experimentation, the piston work was assumed to be negligible because of the high flywheel mass and large range of numerical integration performed on the data. The frictional coefficient was also assumed to be constant. To characterize this engine's energy output, 3 configurations will be analyzed. For configuration 1, where the head and pneumatics were taken off the motor, the goal was to determine the mechanical properties of the motor, meaning the friction coefficient and mass moment of inertia in the system, as well as perform the appropriate energy balance for the systems at 3 speeds. Because the head was removed, the work from air and the work discrepancy were ignored. For configuration 2, where the head was added to the engine, but there was no pneumatic injection, the goal is to determine the work from air, which would be adiabatic only as there is no injected air, and the work discrepancy, which relies on the air work. Once all the work terms were determined, and the goal is to perform a full work energy balance to understand fluid parameters of the motor. And finally, for configuration 3, where the head and pneumatics were added to the system, the goal is to understand how the isobaric process occurring within the motor during air injection affects the air work and discrepancy, and to use this understanding to tune the injection of the engine for optimal power output. Before starting data collection each week, the force transducer and encoder were calibrated. This was important as the systems may have been altered between week to week, between varying lab sections. To calibrate the force transducer, weights were added to a platform attached to the transducer, and the voltage output from the transducer was recorded. This torque was calculated using equation 1 and with the mass and length of the arm, and using a York regression with the calculated torque and recorded voltage measurements, the calibration equation, or equation 2, was found. As seen from the difference in the slope from 0.75 to 0.71 from configuration 1 to configuration 2, this recalibration was necessary. For the encoder, the location of the top dead center, or when the piston was at its highest position, was found, and the encoder was zeroed at this value.
So we begin with our first configuration in which the engine has no head and no pneumatics. Looking at the energy balance equation, we are assuming in this configuration that the work of the piston, the air, and discrepancy work are all negligible for the reasons Taryn mentioned earlier. We also assume that the initial angular velocity is 0 as the system starts from rest. The procedure for this configuration includes starting the engine from rest and allowing it to reach steady state for 5 seconds of data. This is conducted at 3 increasing speeds with all flywheels attached, as well as one of the previous speeds with only one flywheel. The goal for this configuration is to characterize the work done by the motor and the friction, as well as the physical parameters of the flywheel's moments of inertia, which can be compared to theoretical values. Here we have the average torque values collected by the force transducer compared to the angular displacement measured by the encoder for the slow speed trial. Through the use of numerical integration using 10-degree encoder bins, we find the work done by the motor, which can be represented as the area under the curve shown here. The work done by friction is found by the area under the torque offset value at steady state. Again, for the slow RPM trial, the work of friction is represented here. By rearranging the energy balance equation and using the previously determined values of the motor and friction works, the moment of inertia of the flywheel can be calculated. This equation and graphical representation is shown here. This slide showcases the results for all of the speeds and flywheel masses tested in this configuration. Some noteworthy observations include the increasing work related to increased speed, as well as lower work for smaller moments of inertia. Lastly, there are significant discrepancies between our experimental moments of inertia and the theoretical values. While the theoretical value for all the flywheels should be just under 0.01 kilogram meter squared, ours averaged to be 0.0146, which is an extremely large error. This is likely due to the overly simplistic modeling of the theoretical value, which doesn't take into account the shaft of the motor, the bolt nuts, or the possibility of improperly centered weights. In conducting this experiment, we observed the relationship between frictional torque and speed. We found that frictional torque increased with increasing speed, meaning it is inaccurate to model friction is constant across speed settings. This follows the Newtonian model of friction rather than the Coulombic. Lastly, week 1 demonstrated Newton's second law for rotation. Removing the flywheels decreased the time needed to reach steady state, which shows that acceleration decreases and as inertia increases with torque held constant.
For configuration 2, where the head is installed with no pneumatics, we can still assume that work of piston is negligible, as the flywheels are still attached to the engine. However, because the head is installed, we can no longer assume that work from the air is negligible for the whole system. For the intake and exhaust strokes where the valves are open, the work from air can be assumed as negligible, but for the compression and power strokes where the valves are closed, the work from the air must be calculated. The purpose of this portion was to determine the motor, friction, and air work for each of the 4 engine strokes. To ensure this system was run performing at steady state, the engine was run for 5 to 10 seconds before any data was collected at the high, medium, and low speeds. Because there is no pneumatic injection, there is no additional air pushed into the cylinder. Therefore, the piston is adiabatically expanding and contracting within the cylinder, and in theory, the work from the air should be equal and opposite one another for the 2 strokes. Using the following theoretical calculations, the theoretical work was calculated as 22.4 joules.
When zooming into only 2 cycles of the engine in configuration 2, the following plot shows the expected torque and crankshaft angle data for a system with no flywheels, where the clear spike is seen at the compression stroke because the work from the air throws the system out of steady state. The system that includes the flywheels would appear with more noise as the increase in inertia affects how quickly the piston can accelerate and the time it takes to achieve steady state. This plot shows the torque and crankshaft angle data for the experimental no flywheel system, and it is considerably noisier than the expected data shown on the previous slide. It does not show the clear dips at 360 degrees for the compression stroke as expected, although it does contain dips that are 720 degrees apart in certain areas. There is no evident and clear sinusoidal pattern that was achieved. Therefore, it is difficult to determine with confidence the strokes of the engine. The steady state region also cannot be identified. Potential sources of this noise include the head not being installed correctly and the engine not being mounted properly. When operating the engine in the classroom, it was substantially louder during operation than any other engine and shook diagonally at each rotation, as seen in the video. A piece of the motor may not have been mounted properly, leading to additional vibrations of the engine, which translated to the force transducer. With the addition of the flywheels, the system response worsens, which was expected but did not lead to any additional pattern recognition. There are dips in the data that appear at approximately 360, 540, and 1260 degrees, but with the lack of steady state, the data is not clean enough to show the expected pattern. The response for the slow and medium varies more erratically than the fast system. There is no distinct four-stroke of the engine identifiable in this dataset. For each 180-degree segment, the work motor and work friction terms were calculated as in configuration 1 using numerical integration and the Newtonian friction model. Upon calculating the angular velocities at the beginning and end of each 180-degree segment and adding in the appropriate experimentally determined I-fly values, the full work energy equation was manipulated to calculate the experimental work air terms shown in this table. To find work discrepancy, the theoretical and experimental work air values were subtracted as they represent the difference between the theoretical and actual. As the data was noisy and unpredictable, the numbers found in this analysis are largely for the purpose of understanding the analysis process, but we must take caution on making conclusions on this data.
The work discrepancy is calculated by subtracting the work of air from bottom dead center to top dead center of the model from the corresponding experimental value. Thus, this factor takes into account all factors not taken into consideration by the model. Looking at this discrepancy metric, as well as the motor uncertainty, 2 cases emerge. One where the discrepancy is greater than the uncertainty, and one where it is less. For the former, case 1, this indicates an improvement in the model or product is needed, as the uncertainty is adequate to interpret the discrepancy. In the latter, case 2, an improvement in sensors or practice is needed, as effects from uncertainty and discrepancy become conflated. As can be seen within the table, all magnitudes of discrepancy for power and compression phases are greater than the uncertainty, meaning that each belongs to case 1. Thus, improvements in the model are needed as adequate uncertainty resolution is present for the discrepancy to capture the effects of the system. In week 3, pneumatic pressure in the engine will drive the motor to characterize the discrepancy between the model and experimental values and to find the optimal control of injection where motor work is negative, indicating the engine is driving the motor. Week 2's experiment will be rerun to reduce data noise by ensuring that all potential vibration generating fixtures are secured. Final conclusions for this lab include a full work energy model for the engine, an estimate of max work output, and quantization of uncertainty and discrepancy within the system to prove its effectiveness. Thank you.